Hello, in this lecture we'll answer two questions. In the first question, we'll find out the area of this rectangle ABCD, and in the second question, we will find out the area of this green shape that is inside square ABCD. So we start with the first question. In the drawing, we have rectangle ABCD. Beside this rectangle ABCD, we have this semicircle. We also know that this is 9/7 AP, that is equal to 6 units in its length. This is 9/7 PC, that is equal to 5 units in its length. Again, our mission is to find out the area of this rectangle ABCD. So first of all, we know that all the angles inside the rectangle are right angles. So those four angles are all right angles. So actually, this is a right angle. This is also a right angle. This is a right angle. And this is also a right angle. In the next step, we will define the center of this semicircle. This point is point O. We will define the point of tendency of tangent DC with this semicircle. This point is point M. We will define the touching point of this semicircle with side AB of this rectangle ABCD. This point is point E. We will define the radius of this semicircle as x. So the radius of this semicircle is equal to x units according to our definition. So in the next step, we will join points O and M together by a straight line. Point O is the center of this semicircle. Point M is the point of the semicircle itself. Therefore, OM is the radius of this semicircle that is equal to x units in its length according to our definition. And because of the fact that the radius OM, that is equal to x, the radius OM of this semicircle is drawn to point M, that is the point of tendency of tangent DC with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If DC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. So, inside this quadrangle OMCB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that states that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So actually, inside a quadrangle MOBC, inside this quadrangle, we have 4 right angles. And according to rule 5, any quadrangle that has 4 right angles must be this rectangle from the square. So we relate to this quadrangle, it's a rectangle. It's a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle MOBC, side MO must be equal to the opposite side CB, but MO is x, therefore CB must be also equal to the opposite side CB must be also equal to x units in its length. In the next step, we will join points E and P together by a straight line. By joining points E and P, we created the peripheral angle APE. This is the peripheral angle APE. And this peripheral angle APE subtends on AE. AE is the diameter of the semicircle. Why AE is the diameter of the semicircle? Because of the fact that OA is the radius of this semicircle, that is x, and OE is also the radius of this semicircle, that is equal to x. X plus x is 2x. X is the radius, and 2x is the diameter. And because of the fact that this chord AE passes from point O, that is the center of the semicircle, we know that any chord that passes through the center of the semicircle must be the diameter of the semicircle. Therefore, AE is the diameter of this semicircle. So this is the diameter of the semicircle, and you can see that peripheral angle APE subtends on AE, that is the diameter of this semicircle, and we know that according to rule 7, any peripheral angle that subtends on the diameter of the circle or semicircle must be equal to 90 degrees in its size. So I repeat quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees. In the drawing, we have a circle, and AB is the diameter of this circle. This is peripheral angle ACB that subtends on AB, that is the diameter of this circle, and therefore peripheral angle ACB must be equal to 90 degrees in its size. So we already implemented rule 7 in our drawing, because in our drawing we have peripheral angle ACE that subtends on AE, that is the diameter of the semicircle, and therefore peripheral angle APE is equal to 90 degrees in its size according to rule 7. In the next step, we define this angle as alpha. So in triangle APE, in this triangle APE, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this firmness angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in a triangle. Likewise, we focus on the big right triangle ABC. In this big right triangle ABC, this angle equals to alpha, this angle equals to 90 degrees, and therefore this firmness angle must be equal to 90 degrees minus alpha, according to the sum rule that the sum of the angles in any triangle is equal to 180 degrees. Okay. Actually, this is angle A, that is a common angle that belongs to both triangles. Angle A belongs to the big triangle ABC, and angle A also belongs to this right triangle APE. So angle A is a common angle that belongs to both triangles. So in the next step, we prove that the big right triangle ABC is similar to this small right triangle APE. So we prove that those two right triangles are similar to each other. So I write it down. The big right triangle ABC is similar to the small right triangle APE. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So actually this is angle ABC in the big right triangle ABC, or okay, angle ABC. is equal to this angle, that is actually angle APE in the right triangle, triangle APE. So I'll repeat again. Angle ABC in the big right triangle ABC equals to angle APE in the small right triangle APE. They are both equal to 90 degrees and therefore they are equal to each other. In addition, as I already mentioned before, this is angle A, that is a common angle that belongs to both triangles. So we can write down that angle A equals to itself as a common angle that belongs to both triangles. So if we relate to this angle A as it belongs to the big right triangle ABC, it will be defined as angle CAB. And if we relate to this angle A as it belongs to the small triangle APE, it will be defined as angle PAE. Repeat again. This equation means that angle A equals to itself. We just call to angle A two different names. Angle A equals to itself. It's a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees most often, therefore they are equal to each other. So actually, this is angle ACB in a big right triangle ABC, and it is equal to this angle, that is actually angle PEA in the small right triangle APE. Repeat again. Angle ACB, the big right triangle ABC, equals to angle PEA in the small right triangle APA, in the small right triangle APE, and they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually prove that all the three angles of this big right triangle ABC are correspondingly equal to all the three angles of this right small triangle APE. And therefore those two right triangles are similar to each other according to angle similarity rule. So I'll write it down. We actually found out that the big right triangle ABC is similar, this is the sign of similar, to the small right triangle APE according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the right small triangle APE over side AB of the big right triangle ABC is equal to side AP of the side AE of the right small triangle AEP over side AC of the big right triangle ABC. So I'll repeat again. From the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. That side AP of the small right triangle APE over side AB of the big right triangle ABC is equal to side AE of the small right triangle APE over side AC of the big right triangle ABC. Okay. AP is 6 according to what is given us the question, over AB. AB is the missing side, so we leave it as it is. And it is equal to AE. AE is 2x. It is actually the diameter of the semicircle, that is 2x, over AC. AC in total equals to 6 plus 5, that is 11. So AC is 11. So in total, we actually found out that 6 over AB equals to 2x over 11. Here, we of course multiply this equation, and we get that 6 times 11 is 66, and it is equal to 2x times AB. So 66 equals to 2x times AB. Here we will divide this equation by 2, and we get that 66 over 2 is 33, and it is equal to 2x over 2 is x, so it is x times AB. So in total we found out that 33 equals to x times AB. Here we will divide this equation by x. It is allowable to divide the equation by x because x is the radius of this semicircle. It can never be equal to 0. So it is allowable to divide this equation by x. So we found out that AB equals to 33 over x units in its length. AB is the length of rectangle ABCD, and it is equal to 33 over x units in its length. Our mission is to find out the area of this rectangle ABCD. We have to find out the area of rectangle ABCD. Actually, we know that the area of a rectangle equals to the length of the rectangle times the width. Repeat again, the area of a rectangle equals to the length of the rectangle times the width. And therefore, the area of this rectangle ABCD must be equal to the length of this rectangle ABCD times the width. The length of this rectangle ABCD is AB, and the width is CB. So in total, we found out that the area of rectangle ABCD is equal to the length AB times the width CB. AB is 33 over x times CB. CB is x. 33 over x times x. So we have x in the numerator and x in the denominator, so x will get cancelled, and we left only with 33. So if we found out that the area of this rectangle ABCD is equal to 33 square units. So we finished with the first question. In the next step, I will present to you the second question, and we'll solve the second question of this lecture. Our mission in this second question is to find out the area of this green shape. Actually, in the drawing, we have here square ABCD. ABCD is a square. You know that BP equals to PC. So if we define, and we know that the area of this triangle COP is equal to 5 square units in its size. So first of all, again, our mission is to find out the area of this green shape. So first of all, we will define the length of BP as A. And we know that BP equals to PC. So if BP equals to A, then PC must be also equal to A. We know that all the sides of square ABCD are equal to each other. Side BC in total equals to A plus A, that is 2A. Therefore, side AD must be also equal to 2A units in its length. So here we have those angles are defined as vertex angles, and you know that vertex angles are equal to each other. So those two angles are equal to each other. So if this is angle theta, then this angle must be also equal to theta, because they are equal to each other according to the rule that I mentioned, that vertex angles are equal to each other. We have those two angles are defined as alternating angles, and they are located between the parallel lines AD and BC. We know that the opposite sides of a square are parallel to each other. Therefore, in square ABCD, side AD is parallel to side BC. Those two alternating angles are located between the parallel lines AD and BC. And according to Rule 15, alternating angles between parallel lines are equal to each other. Therefore, those two alternating angles that are located between the parallel lines AD and BC must be equal to each other. So if we define this angle as alpha, then this angle must be also equal to alpha, because they are equal to each other according to Rule 15. Likewise, those two angles are defined as alternating angles, and they are located between the parallel lines AD and BC, and therefore according to Rule 15 they are equal to each other. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta, because they are equal to each other according to Rule 15. So it is very easy to see that the small triangle COP is similar to the big triangle DOA. Why? Because they have exactly the same angles. In both triangles we have angle theta, in both triangles we have angle alpha, and in both triangles we have angle beta. Therefore, those two triangles, that is to say triangle POC and triangle AOD, are similar to each other according to angle similarity rule. So I write it down. So triangle AOD, the big triangle AOD, is similar to the small triangle COP. This is the sign of similar. So the big triangle AOD is similar to the small triangle COP according to angle similarity rule. And from the fact that those two triangles are similar to each other, we will derive actually I present to you all 22, and we will implement Rule 22 on those two similar triangles. According to Rule 22, the ratio of the areas of similar triangles is equal to the square of the ratio of their sides. So in the drawing we have triangle ABC that is similar to the small triangle EDF. And therefore, because of the fact that those two triangles are similar to each other, we will derive that the ratio between the areas of those two triangles, that is to say the area of triangle ABC over the area of triangle EDF, is equal to the square of the ratio of their sides. That is to say, it is AC over DE square, and it is also equals to AB over DF square, and it is also equals to CB over EF square. So actually we can implement Rule 22 in our drawing. Why? Because in our drawing we have only found out that the big triangle AOD is similar to the small triangle COP. And therefore, according to the Rule 22, the ratio between the area of this triangle ADO over the ratio of the small triangle COP is equal to the square of the ratio of their sides. That is to say, it is AD over PC squared. The square of the ratio of their sides is side AD over side PC, that is the corresponding sides squared. So in total, according to rule 22, we have found out that the area of triangle ADO over the area of triangle COP is equal to AD over PC squared. So the area of triangle ADO, it is the missing area, so we leave it as it is. The area of triangle ADO over the area of triangle COP. It is given us the question that the area of this small triangle COP is 5 square units. So it is 5 over AD. AD is 2A over PC. PC is A squared. Okay? AD over PC squared. So if we found out that the area of triangle ADO, the big triangle ADO over 5 equals, here we have 2A over A squared. We have A in the numerator and A in the denominator, so A will get cancelled, and we're left only with 2 squared. 2 squared is of course 4. Here we will multiply this equation by 5, and we get that the area of triangle, the big triangle ADO, is equal to 5 times 4, that is 20 square units. So if you found out that the area of this big triangle ADO is equal to 20 square units. Okay. Again, we know that the big triangle ADO is similar to the small triangle COP. And therefore, because of the fact that those two triangles are similar to each other, the following relationship exists between their sides. Side AD of the big triangle ADO over side PC of the small triangle POC is equal to side AO of this big triangle ADO over side OC of the small triangle OPC. And again, because of the fact that those two triangles are similar to each other, the following relationship exists between their sides. AD, side AD of the big right triangle ADO or side PC of the small right triangle POC is equal to side AO of the big triangle ADO or side OC of the small triangle OCP. AD is 2A over PC. PC is A, and it is equal to AO over OC. So here we have 2A over A is 2. So 2 equals to AO over OC. Here we will multiply this equation by OC, and we get that 2 times OC is equal to AO. Read again, if we found out that 2 times OC equals to AO. So if we define the length of OC as B, so we substitute OC by B, we get that 2B equals to AO. So according to our definition, OC equals to B. If OC equals to B, we found out that AO equals to 2B. So if we found out that according to our definition, OC equals to B. If OC equals to B, then OA equals to 2B. Okay. So in the next step, I will present to you another rule and we will implement the new rule in our drawing. The new rule is true in any triangle. So we have here, this is triangle ABC that could be any triangle. If we draw the red line segment AP, it will divide this triangle ABC into 2 parts. The first part is triangle ABP and the second part is triangle APC. The area of this triangle BAP is equal to the base BP times the height edge over 2. Again, the area of this triangle ABP equals to the base BP times the height that is edge over 2. Likewise, the area of this, the second part of this triangle APC, it is equals to the base PC times the height that is edge over 2. Again, the area of this triangle APC equals to the base PC times the height edge over 2. So the ratio of the area of this triangle ABP over the area of this triangle APC, so the ratio of triangle ABP over the ratio of triangle APC, and the area of triangle ABP is BP times edge over 2, the area of triangle APC is CP times edge over 2. So here we have 1/2 in the numerator and 1/2 in the denominator, so 1/2 will get cancelled. We have edge in the numerator and edge in the denominator, so edge will also get cancelled, and we are left only with BP over CP. So in total, we should find out that whenever you divide a triangle, that could be any triangle, but into 2 parts, then the area of the 2 triangles that the ratio between the area of between the 2 triangles that will be created is equal to the ratio between their bases. Why? Because the area of triangle ABP over the area of this triangle APC equals to BP, that is the base of this triangle ABP, over PC, that is the base of this triangle APC. Okay, so the ratio between the areas of those 2 triangles is equal to the ratio between their bases. This is BP over PC. So we can actually implement all the new rule in our drawing. Why? Because in our drawing, if we focus on the big right triangle ADC, this big right triangle ADC is divided into 2 parts by line segment DO. Again, the big right triangle ADC is divided into 2 parts by line segment DO. So we can implement the new rule in our drawing. According to the new rule, we get that the area of this triangle ADO over the area of this triangle DOC is equal to the ratio between their bases. The base of this triangle ADO is AO, and the base of this triangle DOC is OC. So, in total, according to the new rule, we should find out that the area of triangle ADO over the area of triangle DOC equals to AO over OC. Okay, so the area of the big triangle ADO is 20. So we solve the area of triangle ADO by 20 over the area of triangle DOC, that is unknown. So we leave it as it is. And it is equal to AO. AO is 2B over OC. OC is B. So 2 over the area of triangle DOC is equal to 2B over B. So here we have B in the numerator and B in the numerator, so B will get cancelled and we left only with 2. So we should find out that 20 over the area of triangle DOC is equal to 2. So here we will multiply this equation by the area of triangle DOC, and then we will divide it by 2. So we get that the area of triangle DOC is equal to 20 over 2, that is 10. So if you found out that the area of the small triangle DOC is equal to 10 square units. Okay. Actually, the right triangle ADC can go into the right triangle ABC. Why those two right triangles can go into each other? They can go into each other according to side rule. Side AD or triangle ADC is equal to side BC or triangle ABC because it is a square and all the sides of the square are equal to each other. Likewise, side DC of triangle ADC is equal to side AB of this triangle ABC because the sides of the square are equal to each other. And finally, side AC is a common side that belongs to both triangles. So in total, we should find out that triangle ADC can go into triangle ABC according to side rule. So I'll write it down. We actually found out that the right triangle ADC congruent, this is the sign of congruent, to the right triangle ABC according to side rule. And from the fact that those two right triangles are similar to each other, we will derive that they are also the same areas. Okay? So actually, the area of triangle ADC is equal to the area of triangle ABC. Okay? But we know that the area of this triangle ADC in total equals to 20 plus 10, that is 30 square units. So I can write here that the area of triangle ADC is equal to 30 square units, and from this equation 30 equals to the area of triangle ADC equals to the area of triangle ABC. We will derive that the area of triangle ABC must be also equal to 30 square units in its size. Okay, so we derive that the area of the right triangle ABC is also equal to 30 square units in its size. So the area of this right triangle ABC is equal ABC is equal to 30 square units in its size. So if we define the area of the green shape, that is the area that we are looking for in this question, as X, then the area of triangle ABC will be equal to X plus 5. Repeat again, the area of triangle ABC in total it is equal to X plus 5 square units. So write it down. If we found out the area of the right triangle, ABC, is equal to x plus 5 square units. But we have already found out that the area of this triangle ABC is 30 square units. So it is equal also to 30. So from this equation we derive that x plus 5 equals to 30. Here we subtract 5 from this equation, and we get that x equals to 30 minus 5, that is 25. So in total, if we found out that the area of this green shape is equal to x is equal to 25 square units. So until now, if we found out the area of the green shape is equal to 25 square units. And that is the answer to the question. Repeat again. If we found out that the area of this gray shape, that is the area that we are looking for in this question, is equal to 25 square units. So we finish with the second question. In the next step, I will summarize the lecture. We'll start with the first question, of course. In the first question, our mission is to find out the area of this rectangle ABCD. So, in the drawing, we have the big rectangle ABCD. Inside this rectangle ABCD, we have this semicircle. In addition, we know that this is line segment AP, that is equal to 6 units in its length. This is line segment PC, that is equal to 5 units in its length. Again, our mission is to find out the area of this rectangle ABCD. So first of all, we know that all the angles inside rectangle ABCD are right angles. So those 4 angles are all right angles. In the next step, we define the center of this semicircle. This point is point O. Likewise, we define the point of tendency of tangent DC with this circle, with this semicircle. This point is point M, and we define the touching point of this semicircle with side AB of this rectangle ABCD. This point is point E. We define the radius of this semicircle as x. Point O is the center of this semicircle. Point M is the point on the semicircle itself. Therefore, OM is the radius of this semicircle, that is equal to x units in its length according to our definition. The radius OM, that is equal to x, the radius OM is drawn to point M, that is the point of tendency of tangent DC with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO according to rule 1. If DC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. By doing this construction, we created quadrilateral OMCB. This is quadrilateral OMCB. Inside this quadrilateral OMCB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 facing angle, in total they must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4 facing angle must be equal to 90 degrees in its size. So inside quadrilateral MCBO, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So related to this quadrilateral MCBO, is a rectangle. According to rule 5, it is a rectangle, because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle MCBO, side MO must be equal to the opposite side CB. But MO is x, therefore the opposite side CB must be also equal to x units in its length. In the next step, we join points A and P together by straight line. By joining points A and P, We created peripheral APA. This is peripheral EPA. This is peripheral EPA that subtend on AE, that is the diameter of this semicircle, and we know that any peripheral angle that subtends on the diameter of the semicircle or a circle must be equal to 90 degrees in its size, according to Rule 7. So according to Rule 7, this peripheral APE that subtends on the diameter AE is equal to 90 degrees in its size. In the next step, we define this angle as alpha. So triangle APE, the right triangle APE, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees. And 90 degrees plus 90 degrees, it is equal to 180 degrees. It is the sum of the angles in any triangle. Likewise, if we focus on the big right triangle ABC, this big right triangle ABC, this angle equals to alpha. This angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that this is angle A, that is a common angle that belongs to both triangles. Angle A belongs to the big right triangle ABC, and angle A also belongs to this right triangle, triangle APE. So angle A is a common angle that belongs to both triangles. So in the next step, we prove that those two right triangles, the small right triangle AP and the big right triangle ABC, are similar to each other. So why those two right triangles are similar to each other? First of all, this is angle A, this is a common angle that belongs to both triangles. So we can find out that angle A equals to itself is a common angle that belongs to both triangles. In addition, those angles, they are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if we prove that all the fingers in the big right triangle ABC are correspondingly equal to all the fingers of this right triangle AP, and therefore those two right triangles are similar to each other according to angle similarity rule. Again, if we found out that the big triangle ABC is similar, this is the sign of similar to the small right triangle APA according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the right triangle APE over side AB of the right big triangle ABC is equal to side AE of the right small triangle APE over side AC of the big right triangle ABC. Okay, again, we will derive that side AP of the right small triangle AP over side AB of the right big triangle ABC is equal to side AE of the small right triangle APE over side AC of the big right triangle ABC. AP is 6, AB is the missing side, so we leave it as it is. AE is 2x, it is the diameter of the semicircle, that is 2x. And AC in total equals to 6 plus 5, that is 11. So AC is 11. So in total we found out that 6 over AB equals to 2x over 11. Here we cross multiply this equation. So we found out that 6 times 11 is 66. That is equal to 2x times AB. So 66 equals to 2x times AB. Here we divided the equation by 2. And finally found out that 66 over 2 is 33. 2x over 2 is x. So in total this expression equals to x times AB. So if we found out that 33 equals to x times AB. Here we divided this equation by x. It is allowable to divide the equation by x because x is the radius of this semicircle. So it can never be equal to 0. So we divided this equation by x, and we found out actually that AB equals to 33 over x. AB is the length of this rectangle ABCD, and it is equal to 33 over x units in its length. Our mission is to find out the area of this rectangle ABCD. Okay, our mission is to find out the area of rectangle ABCD. Actually, we know that the area of any rectangle equals to the length of the rectangle times the width. And therefore, the area of this rectangle ABCD must be equal to the length of this rectangle ABCD times the width. the length of this rectangle ABCD is AB and the width is BC. So in total, we found out that the area of rectangle ABCD equals to AB times CB. AB is 33 over X, CB is X. So in total, the area of rectangle ABCD equals to 33 over X times X. We have X in the denominator and X in the denominator, so X will get cancelled, and we left only with 33. So in total, we found out that the area of this rectangle ABCD is equal to 33 square meters. Now we finish with the first question. In the next step, I present to you the second question, and we solve the second question of this lecture. Our mission in this second question is to find out the area of this grain shape. So in the domain, we have square ABCD. We know that line 7 BP equals to line 7 PC. We also know that triangle POC, the area of this triangle POC is 5 square meters. Again, our mission is to find out the area of this grain shape. Okay. So first of all, we know that those two angles are defined as vertex angles, and we know that the vertex angles are equal to each other. So if this angle is theta, then this angle must be also equal to theta, because they are equal to each other according to the rule that I mentioned. In addition, those two angles are defined as alternating angles, and they are located between the parallel lines AD and BC. Why AD is parallel to BC? Because of the fact that ABCD is a square, and we know that the opposite sides of a square are parallel to each other. Therefore, AD is parallel to BC. So those two alternating angles are located between the parallel lines AD and BC, and therefore they are equal to each other according to rule 15. So if this angle is alpha, then this angle must be also equal to alpha, because they are equal to each other according to rule 15, that states that alternating angles between parallel lines are equal to each other. Likewise, those two angles are also defined as alternating angles, and they are located between the same parallel lines AD and BC. And according to rule 15, they are equal to each other. So if this angle is beta, then this angle must be also equal to beta, because they are equal to each other according to rule 15. So we shall find out that the big triangle AOD is similar to the small triangle POC according to angle similarity rule. That is to say, in both triangles we have angle alpha, in both triangles we have angle beta, and in both triangles we have angle theta. So all the triangles of the big triangle AOD are correspondingly equal to all the triangles of this small triangle POC. Therefore, those two triangles are similar to each other according to angle similarity rule. So I repeat again, the big triangle AOD is similar to the small triangle COP according to angle similarity rule. And from the fact that those two triangles are similar to each other, we will derive that the ratio between the area of this triangle AOD over the area of this triangle POC, the ratio between the area of triangle ADO over the area of triangle COP is equal to the square of the ratio between their sides. That is to say, it is side AB over side PC squared. Side AD over side PC squared, according to rule 22. Okay, so the area of triangle AOD is the missing area, so limit is CTs over the area of triangle COP. It is giving us the question that the area of this one triangle POC is 5 square meters. So we substitute the area of triangle COP by 5, and it is equal to AD. AD is 2A over PC. PC is A, so it is 2A over A squared. So in total, if we found out that the area of triangle ADO over 5 equals to 2A over A squared. A over A is 1, so A will get cancelled, and we're left only with 2 squared. 2 squared is of course 4. So in total, if we found out that the area of triangle ADO over 5 equals to 4. We multiply the equation by 5 and finally found out that 5 times 4 is 20. So if we found out that the area of the big triangle ADO is equal to 20 square units. Repeat again, the area of this big triangle AOD is equal to 20 square units. Okay? And because of the fact that those two triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AD of triangle ADO over side PC of the small triangle POC is equal to side AO of the big triangle AOD over side OC of the small triangle OCP. And again, from the fact that those two triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AD of the big right triangle AOD over side PC of the small right triangle POC is equal to side AO of the big triangle AOD over side OC of the small triangle AOC. Okay? Small triangle POC. So AP over PC equals to AO over OC. AP is 2A over PC. PC is A. So AP is 2A, PC is A. So 2A over A equals to AO over OC. 2A over A is A. 2A over A is 2. So A will get cancelled. So 2 equals to AO times OC. Here we multiply this equation by OC. And finally found out that 2 times OC equals to AO. Okay? So if we define OC as B, so we solve OC by B here, we get that AO equals to 2B. So in total, if we found out that if we define the length of this line segment OC as B, then the length of this line segment AO will be equal to 2B. In the next step, I presented to you a new rule and we implemented the new rule in our drawing. According to the new rule, here, this is triangle ABC that could be any triangle. If we draw the right line segment AP, it will be divided triangle ABC into two parts. The first part is triangle ABP and the second part is triangle APC. So the area of this triangle ABP is equal to the base of the triangle that is BP times the height that is edge over 2. And repeat again, the area of this triangle ABP equals to the base BP times the height edge over 2. While the area of this triangle APC is equal to the base that is PC times the height that is edge over 2. So the ratio between the areas of those two triangles, that is to say the area of triangle ABP over the area of triangle APC, is equal to the area of triangle ABP that is BP times edge over 2 over the area of triangle APC that is CP times edge over 2. We have 1 half in the numerator and 1 half in the denominator, so 1 half will get cancelled. We have edge in the numerator and edge in the denominator, so edge also will get cancelled. And we left only with BP over CP. BP over CP. So I can found out that the area, the ratio between the area of this triangle APB over the area of this triangle APC equals to the ratio between their bases. That is to say, it is equal to BP over PC. BP is the base of this triangle ABP and PC is the base of this triangle APC. So whenever you divide the triangle into two parts, then the ratio between the areas of the two triangles that you created by following the red line that divides the triangle into two parts, the ratio between the areas of the two new triangles will be equal to the ratio between their bases. Because of the fact that the area of triangle ABP over the area of triangle APC equals to the ratio between the base of this triangle ABP, that is BP, over the base of this triangle APC, that is PC. So we can actually implement the new rule in our drawing. Why? Because in our drawing, this is the big triangle, triangle ADC, the big right triangle ADC. We have this line segment DO that divides the big triangle ADC into two parts. The first part is triangle AOD, and the second part is triangle COD. And according to the new rule, the ratio between the area of this triangle AOD over the area of this triangle ODC will be equal to the ratio between their bases. That is to say, the base of this triangle AOD is AO, over the base of this triangle OCD is OC. So in total, we actually found out that the area of triangle AOD over the area of triangle DOC is equal to the base of triangle AOD, that is AO, over the base of triangle DOC, that is OC. Okay. We already found out that the area of this triangle AOD is 20. So we substitute the area of triangle AOD by 20 over the area of triangle DOC, that is unknown. And it is equal to the ratio between their bases, that is AO over OC. AO is 2B and OC is B. Okay. So here, so I found out that 20 over the area of triangle DOC equals to 2B over B. 2B over B is 2. So 20 over the area of triangle DOC equals to 2. Here we multiply this equation by the area of triangle DOC and we divide it by 2, and finally found out that the area of the small triangle DOC is equal to 20 over 2, that is 10. So we found out that the area of this small triangle DOC is equal to 10 square units. We know that this is triangle ADC. This is congruent to this triangle, triangle ABC. Why those two triangles are congruent to each other? They're actually congruent to each other according to side rule. Okay? Side AB equals to side DC. Side AD equals to side BC because it is a square, and AC is a common side that belongs to both triangles. So those two triangles congruent to each other according to side rule. And from the fact that they congruent to each other, we will derive that the area of this triangle ADC is equal to the area of this triangle, triangle ABC. And again, from the fact that triangle ADC congruent to triangle ABC, we derive that they have also the same areas. That is to say, the area of triangle ADC is equal to the area of triangle ABC. But we already found out that the area of this triangle ADC is equal to 20 plus 10, that is 30. So we can write here that the area of triangle ADC equals to 30 square units. And from this equation, 30 equals to the area of triangle ADC equals to the area of triangle ABC. We will derive that the area of triangle ABC is equal to 30 square units. So the area of triangle ABC is equal to 30 square units. But the area of triangle ABC equals to x plus 5. So the area of triangle ABC equals to x plus 5 from one side, but from the other side we already found out the area of triangle ABC equals to 30. So from this equation, we derive that x plus 5 equals to 30. Here we subtract 5 from this equation, and we found out that x equals to 25. That is to say, the area of this green shape, that is x, is equal to 25 square units. Okay, thank you very much.